All right, let's get into it. Today, we're going to pull back the curtain on the invisible architecture that's inside literally every single piece of tech you own. We're talking about the secret blueprint for your computer chip.
So let's start with a question. What could a massive, towering skyscraper possibly have in common with the tiny, powerful phone that's sitting in your pocket right now? Well, the answer is pretty simple. They both start with an absolutely meticulous blueprint.
You know, in the world of chip design, they call that blueprint phase place and route. It's this mind-bogglingly complex process of taking a digital idea, the chip's design, and figuring out how to physically arrange millions, sometimes billions, of tiny components and wires onto a little slice of silicon. But hang on, before you can even think about laying a foundation, doesn't matter if it's for a skyscraper or a microchip, you have to inspect the blueprints. You have to be sure every single little detail is perfect. And that right there is where our main topic comes in. In chip design, this whole inspection process is called a sanity check. It's a whole series of automated checks that engineers run to catch what could be catastrophic errors before they start the super expensive and time-consuming manufacturing process. It's all about finding and squashing those bugs early.
So here's the deal. This isn't just one check, not at all. It's a whole suite of them. Today, we're going to walk through 5 of the most critical inspections that make sure a chip's blueprint is rock solid. Check design, check netlist, check dash timing, check unique, and time design.
Okay, let's start at the very beginning with the checks that look at the foundational master plan itself.
These first 2 commands, check design and check netlist, they're your absolute first line of defense. Think of it like making sure the architect's parts list is complete and that the basic wiring diagrams actually make sense before you go any further. They're scanning for missing info and just fundamental, show-stopping errors.
Now let's talk about one of the first major red flags check netlist is hunting for, something called a multi-driven net. And this is a big problem. It's where you have more than one component trying to shout down the exact same wire at the exact same time. And this visual just explains it perfectly. Imagine 2 light switches on opposite sides of a room, both wired to the same light bulb. Now, what happens if one switch tries to turn the light on while the other tries to turn it off? Right, you get a signal conflict, total confusion, and the system just breaks. That's a multi-driven net. Another one of these classic flaws designers are always on the lookout for is the floating input. This happens when a part is designed to receive a signal, but oops, somebody forgot to actually connect a wire to it. It's just floating there, totally unconnected.
The real danger with a floating input is that it can act like a tiny antenna, just picking up random electrical noise from everything around it. It's like installing a light switch on the wall, but forgetting to connect it to the building's main power. It's completely useless, and worse, if it picks up some stray signal, it could behave in wild, unpredictable ways. Okay, now for a really serious one, the combinational loop. This is a truly vicious cycle, where a signal's path actually loops back and feeds into itself. But there's no clock, no gatekeeper, nothing to regulate it. So the signal just goes around and around and around in this chaotic, uncontrolled feedback loop.
To get a feel for the kind of chaos this causes, imagine that emergency alert system in our skyscraper. The all-clear signal gets sent out, but because of a tiny wiring flaw, that all-clear signal loops back and accidentally triggers the main alarm, again, which then sends another all-clear, which triggers the alarm, forever. It's a complete meltdown. That's a combinational loop.
And finally, for this section, we have the undriven port. Now this is a little bit like a floating input, but it's specifically about the ports on the edge of the chip. It's an input that's been declared in the design, but there is absolutely nothing connected to it. It's a complete dead end.
This is just as simple as it sounds. It's like having an input jack for security camera 5 on your main security monitor, but you never actually installed or connected a 5th camera. The port is there, but it's not getting any signal and it's not serving any purpose. Sanity checks flag this just to make sure it was on purpose and not a mistake. Okay, so we've checked the static blueprints for any obvious wiring mistakes. But a chip, just like a skyscraper, isn't a static thing, right? It's a dynamic system. It has a rhythm, a pulse, and that is all about timing. And let me be perfectly clear about this. In a chip, timing isn't just important, it is everything. The speed of your device comes down to billions of signals arriving at exactly the right place at exactly the right time, down to the nanosecond. It's crazy. The check timing command is the sanity check for this whole rhythm. It's looking for things like missing clocks, which are the very metronomes of the chip, and other issues like unconstrained endpoints or missing delays. It's kind of like checking our skyscraper's internal logistics. Are the elevator schedules all defined? Do we know exactly how long deliveries are supposed to take?
A signal's journey inside a chip is a high-stakes timed event. So, check timing makes sure that the time limits for this journey are all clearly defined. The designers have to spell out exactly how long a signal is allowed to take to get from an input, go through a processing unit, and get to an output. Without those rules, you just have chaos. It'd be like not knowing if it takes 30 seconds or 30 minutes to get from the lobby to the penthouse. You just can't operate that way. All right, so once the basic wiring and the timing plans are looking solid, the engineers perform one final quality control. It's like the last sign-off on the blueprint before construction gets the green light.
These last two checks are super quick, but they're absolutely crucial. First, check unique just confirms that the entire wiring diagram is structurally valid and isn't a duplicate of some other part. Then, time design does a preliminary speed test. It actually calculates the theoretical timing of the chip assuming there are no wires. This tells engineers if the design is even potentially fast enough to hit its targets before they spend weeks arranging the actual physical layout.
So, from conflicting signals to chaotic feedback loops and the vital rhythm of a clock, these sanity checks are really the unsung heroes of the digital world. They're the inspectors poring over the blueprints, making sure that foundation is perfect before a single piece of silicon ever gets touched. So the next time your phone or your computer just works flawlessly, take a second, will you? Think of the dozens of invisible checks, the silent guardians of logic that made it all possible.